I am Mr. Ish and I welcome you to this video. Thank you for joining me. Very recently I presented a video on limits, the study of limits, but for the high school math level, and many of you students will be introduced to limits in that high school math class, especially those students who are studying in the British education system. Limits and calculus are introduced normally in that high school level, and in the American high school level, if you're doing AP Math or AP Calculus, then you will certainly see this in your 12th grade. When I presented that video on limits, it was from a general basis of understanding. Here we're talking specifically about this direct substitution property of limits. And this direct substitution property, I personally like to just abbreviate it as this direct substitution property. Why do you want to know this? Because this is your shortcut for many of the limit questions. For those questions which are involving functions which are polynomials, rational functions, trigonometric functions, and radicals. Your radical functions will be things like this, where you have a radical and you have some sort of function in here. It could be anything, even a polynomial or trigonometric, but you have a radical involved. For these polynomials, rational functions, trigonometric functions, and radicals, if a, limit as x approaches a, if this a falls in the domain of any of these four functions, then just plug this a value right in here into your function, whatever it is your output, that right there is your answer to that limit question. So keep that in mind. For these four types of functions, this right here is your shortcut, the direct substitution property. Again, I'll say for polynomials, for rational functions, trigonometric functions, and radicals, if a, the value a that you're examining for your limit, is in the domain of that function, very easily and clearly it falls in that domain, just plug into your function, just like you would a basic function question. You're plugging in the value and seeing what your output is. That output is your answer to that limit question. It makes sense now to look at all of these four in terms of very quick examples, because this right here, this specific property topic is not hard to understand at all. Let's look at this first one. We're looking at the polynomials first. The polynomials are the most easy to understand because there's absolutely no way that you can zero out your denominator, or you can make your function undefined, or you can have a radical with a negative number, a square root with a negative. You can't. Everything you plug in here, everything will be legitimate value. The domain of polynomial function is almost always minus infinity to infinity. So anytime you're looking at this a value, this a, you can easily just plug it in into places of x. And that right there is your direct substitution property for polynomials. Just plug this 2 right over here in places of x. You'll have a 2 times 2 cubed, which is an 8, minus 3 times 2 plus 1. What is your answer? You have a 16 minus 6 plus 1, 11. So therefore, limit as x approaches 2 for this function will approach 11 in terms of your output. If you had a specific graph of this, I don't know what the graph looks, but at the value of 2 you'll have an output, your range value of 11, and your question will have been solved. And it's that easy for polynomials. Let's look at one more question. Limit as x approaches 3. We have this function right here, 2x minus 3 whole square. And what is this approach? Again, if you were to expand this out, you'll have a quadratic equation. Quadratic equation in terms of a graph is a parabola. But again, this parabola here would have a domain minus infinity to infinity, and 3 is very easily found in this domain. Remember, if a is found in the domain of your function, this right here is your function, then just plug in the value and see what you get. You'll have a 2 times 3 minus 3 and then whole square. You have a 6 minus 3, which is a 3 whole square, and your answer will be 9. So this question has been done. Again, the direct substitution property helps you out. It makes things very easy for polynomial functions. So we've looked at polynomials. Let's look at radicals next. Alright, let's look at this. Limit as x approaches 0. We have this radical function 1 minus 2x in a square root. If you don't know what the graph looks like, it doesn't matter. Just plug this value in right here and see if you make it undefined. If you were to plug the 0 in here and you ended up with a negative in the square root, you know it's not in the domain. But here when I'm doing 1 minus 2 times 0 in a square root, I'm getting a square root of a 1. And I know now, just by looking at this and doing this easy computation, the direct substitution property is working over here. Because 0 gave me a good answer, I know 0 was in the domain of this function, and therefore I can just easily substitute in here. Whatever I get is my answer for that limit question, and I am good. Now look at the same question here. Limit as x approaches, let's say 3. 1 minus 2x. Now if I don't know what the graph looks like, but in general you can figure it out, just find the 0 of this function. 1 minus 2x equals 0, minus 2x is equal to minus 1, and then x is equal to 1 over 2. I know at this 1 over 2 comma 0, if I were to put 1 over 2, I'll have a 0 over here. I'm really looking at something which is looking in that direction. If I were to put 0 in place of x, I have a square root of 1, which is 1, so I know I'm looking at 0 comma 1. My graph looks like this. So all the values here in terms of the domain are minus infinity going all the way up to 1 over 2, including 1 over 2. But here I'm looking at a value 3 which is outside the domain, so I cannot use this property over here. It won't work, because if I put 3 over here, what am I going to get? I'll get a negative radical. I'll have 1 minus 6, which is a root of minus 5, and you can't do that. But again, if you couldn't figure out the graph, you don't have to. Just plug this in. Are you getting a legitimate answer or an undefined answer? Here I'm getting an undefined, therefore it was not in the domain. A value was not in the domain of function, so I couldn't do it. I couldn't utilize this direct substitution property. But because 3 does not fall within the curve over here at all, my answer here would be D and E. The limit does not exist, because there is no limit for this function at 3, because the graph never even makes it up to 3. So this question has been done, and now you can see how it is for radical functions. If A is in the domain of your function, plug it in and you're good. If A is not in the domain of your function, very likely you're having an answer where your limit does not exist. Let's look at trigonometric functions next. Remember, we had 4 types: rational functions, polynomials, radicals, and trigonometrics. Let's look at trigonometric functions. If this value falls in the domain of these functions, you're good. You know, sine and cosine are infinite curves. They go from minus infinity to positive infinity, because that snake-like curve goes in both directions, minus infinity to positive infinity. In both instances, pi over 2 is in the domain of both of these. You can just plug pi over 2 right here in places of x. You'll have sine pi over 2 plus cosine pi over 2. Cosine pi over 2 is a 0, but sine pi over 2 is 1, and your answer is 1. The direct substitution property made it easy. Limit as x approaches this value, this entire function will approach the value 1 in terms of the y value, and your answer would be good. How about this? Limit as x approaches is 0 in the domain of x. Is this a value in the domain of tan? It certainly is. You remember the tan, just a single wave of the tan. You have pi over 2 minus pi over 2. Your function looks like this. 0 right here is in the domain, because your curve is going through the 0. All you do is just plug it in on your calculator. Tan of 0 is a 0. Your answer is a 0, and you're good. Let's look at this. Limit as x approaches pi over 2 tan x. Now, is pi over 2 in the domain of tan? No, it isn't. If you take 90 degrees and you tan it, you get undefined. Why do you get undefined? Because you have a vertical asymptote. In this particular instance, this a value right here, pi over 2, is not in the domain of tan x. So you can't have a clear answer, but you can do a limit from one side. At least the curve is making its way to pi over 2. It's not like pi over 2 is not at all close to it. You have another asymptote over here, and then you have another portion of the curve. When you're looking here at the pi over 2 here for the tan function from the left, you have a certain answer. When you're looking at it from the right, you have a certain answer, because from the left side your curve is going upward, from the right side towards pi over 2 your curve is going down. So you may not have a two-sided limit at pi over 2 where you could say it does not exist, which indeed would be a right answer, but then you can evaluate this for individual one-sided limits, and let's do that. You can do individual one-sided limits because the curve makes its way towards pi over 2 from the right and left, but in both different directions. Limit as x approaches pi over 2 from the left. Your curve is going to go up towards positive infinity. You see how this curve is going up towards positive infinity, and that right there would be your answer. Now the other sided limit. Limit as x approaches pi over 2 from the right. As you're approaching pi over 2, this other tan curve is going down here. For tan x, it's going down towards minus infinity, and you would have two answers. From the left side it's positive infinity, from the right side it's negative infinity. But in general, limit as x approaches pi over 2, you see there's no positive or minus. Tan x, because the left side and the right side limits are not the same, you can say the limit does not exist, because the left side and the right side limits are not the same. How could you have done this without a graph, by means of a calculator only? I'm looking here at a value 90 degrees. From the left side you can just pick a value 89.999. From the right side you can pick a value 90.0001 and see what happens when you plug these in terms of tan. If you actually, you know what, I'll fill the entire screen. If I'm doing a left side value close to 90, 89.999, all that, and I tan it, I'm getting an extremely large number. If I add more 9s, it will become more and more close to positive infinity. From the right side, I'm picking a value 90.0000 and then 1, Add more zeros if you can, but tan it, you'll get a minus very large number. So it confirms you're getting a minus infinity. So again, the direct substitution property helps you out for those instances where that a value is in the domain. Just plug it away and what you get is your answer. But in those instances where it's not in the domain, you have to do some work. And that work involves you to evaluate right side, left side limits, all of that, and maybe use a calculator for approximations. We have one more function to look at, and that's rational functions. The first question we're doing is limit as x approaches 0, we have 1 over x plus 1. How do you know if this a value is in the domain? Find the 0 of your polynomial in the denominator. X plus 1 is equal to 0, x is equal to minus 1. X equals minus 1 would represent a vertical asymptote, but 0 is not the same as minus 1, so this is in the domain of this function. Because if you were to graph it out, you'd have here a vertical asymptote. You'd have a horizontal asymptote too, but we're only looking here at vertical asymptotes. So x approaching this a value of 0 is in the domain because this 0 is not this 0 of your function. It does not zero out your denominator. You can just plug this value right here. You'll have 1 over 1 and your limit answer is 1 and the direct substitution property worked. Let's look at another question. Limit as x approaches 3, we have 2x over 3x plus 5. Here's a rational function. Does this 3 fall in the domain? Sure it does. Find the 0 of this function. 3x plus 5 is equal to 0. 3x is equal to minus 5. We're finding the 0 of the denominator. X is equal to minus 5 over 3. We know we have a vertical asymptote at minus 5 over 3 because minus 5 over 3 will 0 out your denominator and you'll have undefined. This value here is a vertical asymptote. It's not in the domain. But 3 is not minus 5 over 3, so this is in the domain. You can just plug this here in places of x. You'll have 2 times 3 over 3 times 3 plus 5. You'll have 6 over 9 plus 5, which is 14, and your answer here would be 6 over 14, or you can simplify it, 3 over 7. Limit as x approaches 3, this rational function will approach 3 over 7 and your answer will be good. Direct substitution property worked here in both cases. Let's just end this video with one question of a rational function where this is not in the domain. If you find the 0 of that denominator, 5 minus x is equal to 0, minus x is equal to minus 5, x is equal to 5, x equals 5 here represents a vertical asymptote. And you know you have a vertical asymptote here and this a value is your vertical asymptote, so you cannot just plug this in here. You can't, because you'll end up having a 5 over a 0 because you can plug 5 here and 5 here and this is undefined, so you can't do it. So now you have to do work. But what does this work involve? Well, the work can involve you graphing it out and visually from the graph determining your answer, or you can do it from both the left side and you can do it from the right side, but by means of a calculator. And there's nothing wrong with you doing a calculator work over here. And we will do it here by means of a calculator, and you'll probably have an answer here in terms of an infinity. Anyhow, as I showed you, you cannot put 5 over here, so for technically here you'd say your limit does not exist because your a value here is part of your vertical asymptote in terms of being outside your domain. But if you were to pick a value here on the left side of 5, you see how you're approaching this x equals 5 vertical asymptote from the left side, from the right side. What's a value close to 5 from the left side? How about 4.999? What's a value close to the right side? It would be 5.0001. But the more 9s and the more zeros you can add, the closer will be your answer to the true limit answer. Let's look at this left side. Limit as x approaches 5 from the left. We'll have to take these 4.999s and plug them in places of x. I'll put it here in the denominator first. 5 minus 4 point, and I'm going to squeeze out all the 9s. I'm getting this 1 exponent minus 9, and I'm going to save that. Now I'm going to take that same 4.9 in the numerator, squeeze out all the 9s, divided by the denominator, and what I get an extremely large value. That tells me from the left side, this function as x approaches 5 will approach positive infinity. And that one-sided limit answer will be fine. Now let's do this side. We have 5.001s to put. We'll do the denominator first. We'll do 5 minus all the zeros we can squeeze with that 1 at the end. And I'll save this answer. Then I take that same approximated value, 5.000 and 1s, divided by my saved denominator value. And I get minus extremely large number. And that's telling me here, it's a minus infinity. In general, as x approaches 5, you don't have a limit here because the left hand and the right hand limits are not the same. But individually, as one-sided limits, you do have a value, positive infinity, minus infinity. If you wanted to do this by the graph approach, you can, and we can graph it out, but you'd have to be able to determine the asymptotes. We know one asymptote here is x equals 5, which is right here. vertical asymptote, there is a horizontal asymptote. If you take the numerator and you divide it by x, you take the denominator and you divide it by x, you can get a horizontal asymptote. You'll have a 1 over here, then you'll have a 5 over x minus 1. Limit as x approaches infinity, this will zero out. You'll have a 1 divided by minus 1, which is a minus 1. You have a horizontal asymptote here of minus 1. If you don't understand here how I calculate a horizontal asymptote, it's no big deal. We can do that in a video in the future. If you want to see and plug x as 0, you'll have a 0 divided by 5. You know the origin is involved. You have a curve which is coming now, something like this. Like this, right here. Bidirectional curve. Horizontal, vertical asymptote. Limit as x approaches, this right here is my 5, right here. You see this value right here, 5, that right there is my value that I'm approaching here. Limit as x approaches this value here of 5, which is a vertical asymptote. From the left side, it's going here towards positive infinity, and that's exactly what we have, so we're right. Limit as x approaches 5 from going down here towards minus infinity, and that's exactly what we have, and it's right. You can do this by calculator approach, an approach which I recommend because not everyone can generate a graph. Always pick the right and left side values very close to that a value and plug it into your function and see what you get. Your output can easily be something like this, and you go with that. Or you can do the graphic approach, read your curve, your graph, how it behaves, and that right there is your answer. Here are 2 ways of doing it. In general, the answer for this is really does not exist, but if your teacher asks you to present both the left and the right side values, this is how you do it. Approximation or graph. And that's it for this video. You've seen the direct substitution property here at work. If a is in the domain of your function, plug it in. What you get is your answer. If a is not in the domain of your function, you have some work to do, and that work can involve something like this. Have a good day then. Bye.